So hi, I'm Rich Porter. I've got a short presentation here on using open source tools for chip verification. These tools do not primarily target functional verification as such, but can do useful work for it nonetheless. My experience is with all digital verification, but most of these tools should also work for the analog and mixed signal development too. Yeah. Okay, I need to start by pointing out that you probably already use lots of open source tooling and that using new tools is thus not an issue in itself. I'd like to introduce you to some new tools. I believe it's desperately important to keep current with technology, and I don't mean using it promiscuously in production. If you do, your repositories will be littered with fragments of code in fleetingly fashionable languages. I mean keeping up to date and knowing what's available so you can use it when you need it. Hopefully by piquing your interest now with some recent but mature tooling, you will hopefully become aware of it and be able to use it in the right circumstance at some point in the future. If I introduce everyone to just one new tool today, then this presentation will have done its job. It may be free as in freedom, but it certainly isn't free as in beer. There are costs associated with installation, education and maintenance, even if there is no cost in licensing. But those costs do exist with any tool. There's a lot of abandonware, half-finished projects, and multiple projects which aim to do the same thing. But a core of very high-quality software exists, produced by very talented engineers and shared with us by them and their employers. A large community of users means the software has been used in many places and then debugged by another set of very talented engineers who have contributed fixes and features. You're unlikely to find a new bug in a large mature project like Python or Git, but if you do, you can fix it and contribute that fix as well as new features. You can also change the code and not be bound to contribute those changes if you just use them internally. I haven't added a why not open source slide. I'm not going to discuss this today beyond stating that the GPL is not viral. If you do use these tools internally, you're not distributing any executable, so you don't need to make any source publicly available. Although some open source tools are not fee-free when used commercially, so you do need to check the licenses in that respect. These are probably used globally by everyone here, although I have come across several ASIC firms that are developed on Windows. GNU Linux, although some people may have used Open Solaris or FreeBSD. The venerable Emacs in Vi, although some people may use the Nirvana editor, and Eclipse has been mentioned already for those people that like IDEs. Revision control with RCS and CVS. RCS isn't quite outdated yet. It still has its place. If you look in users' bin directories, you'll see that the more savvy engineers will probably have their scripts under RCS control. Mozilla web and email clients, Firefox and Thunderbird. Old school scripting with TCL and Perl, and X-Windows libraries and window managers. But what's new? So version control. Concurrent version systems, CVS, was first released more than 20 years ago in 1990, and I think it's now well past its best before date. So version dates from 2000 and seems to have gradually replaced CVS. The repository is now the unit of change and not the file like CVS. So meaningful file-wise changes get grouped together in a single revision. But you still need to be connected to the central repository to make commits and see older versions and log comments. So version does make branching and merging somewhat less fraught than CVS. However, the process has changed a lot since the introduction of distributed version control systems. These three were all initially released within days of each other in 2005. With these distributed version control systems, you can make many local commits to your local checkout before pushing them back to the master at a later date. Branching and merging is the working mode, and revisions are identified by MD5 sums as opposed to incrementing version numbers. A local fork or checkout contains all the history, so no connection to the master is required to push local commits and pull other updates. Bazaar is Python and C based. It was originated internally at Canonical the company that also distribute the Ubuntu flavor of Linux. Mercurial is Python and C-based as well. Git is written in C. It was famously created by Linus Torvalds and has seen a massive uptake, especially with the likes of GitHub.com. I know that there's local traction in the Bristol DV community with Mercurial and Git. I don't think it really matters which one you use as long as it isn't CVS. They all do the same thing. Mercurial has a Subversion plugin to enable the use of Subversion as a client, and I think there's similar functionality with Git and Mercurial as well. On a slightly different versioning note, there's also a simple program that allows tool versioning. If you haven't heard of it, I suggest you look at modules. It allows you to simply load and unload different tool versions into your shell environment. Everybody needs to use a tool like this. It's especially useful when you have multiple EDA tool versions installed. Nats, Bugzilla, and Mantis all work, as do Twiki, Moin Moin, and the other wiki packages. But an integrated call tracker and wiki and version control system can do much more. It allows markup in the wiki content as well as call descriptions and commit comments. So in a call you can reference a commit number, and in a commit comment you can reference a call number. This allows a click-through between call, commit, source code and wiki via the web interface. These are still a bit immature as it doesn't force a number to be given or check the relationship between commit and call number is the same. But it is useful to determine why code exists when clicking through on a code browser to the commit comments, to the call history and back again. It's also easy to set up and maintain just one thing than a separate wiki and a call tracker. GCC is in the GNU compiler collection. The supported languages include Ada, C, C++, Objective-C. It also contains GDB and gprof, the debugger and profiler. The formerly low-level virtual machine, LLVM, has been ready for a number of years and is now gaining traction. The free BSD now is now built with it by default. CLang, the compiler built upon the LLVM, promises reduced memory footprint and increased compiler speed whilst being GCC compatible. Profiling is key for everything, simulations and infrastructure. If you don't keep tabs on where time is spent, performance will slowly degrade as new features are added. I'm not advocating continual optimization, but looking for large step decreases in performance to avoid the later exclamations of "it never used to be this slow" and the realization that it could have been any change or check-in since the start. Vulgrin's memcheck option catches segmentation faults and carries on if it can, while memory leaks, hanging pointers, and other memory-related programming errors can also be caught. Vulgrind also has cache grind and call grind options for performance profiling. The tool works by replacing the malloc and free system calls as well as load store instructions, but this does slow execution down. But it's an invaluable tool to find memory-related problems. The Google Perf tools provide leak detection with the thread caching malloc and a separate profiling library. The profiler uses a sampling approach so slowdown is minimized. Nice graph output is provided in a variety of formats with graph viz. I always leave some form of profiling on in at least some tests by default to check for regression in performance, as it makes looking for the cause much easier as the regression will have occurred recently. Make is probably still the best option for source code compilation, but don't try and use Makefiles for anything else. Beware of Make Regression or Make GDS2. I've seen both. Remember that sometimes just recompiling a single file might be quicker and without dependency bugs. Ccache caches object files by spotting similar commands, objects, and options in files. This can help improve speed a lot. It's also trivial to install with modules, command that I mentioned earlier, and can slash compile and link times if you make clean or build from a clean checkout regularly. SCons is a Python-based build tool with Python expressiveness and extensibility. It also has some built-in Ccache-like functionality. Hudson Jenkins is a continuous integration tool. It can provide very early feedback on a broken repository by compiling and running tests at every commit. When did it stop working is a common question without continuous integration. Jenkins can be easy to get started with, and even if you just compile and run a simple hello world test, it's light years better than not checking at all. Don't forget a scheduled nightly build too to check for other sources of bit rot. The majority of companies will have a compute farm, although some I now call them a private cloud. Batch queuing system is often used to allocate jobs to machines. Sun Grid Engine has been widely used. Multiple forks now exist, especially since Oracle's acquisition of Sun. OpenLava is a fork of Platform LSF Lite. I personally haven't used this one. But both support the Distributed Resource Management Application API, or DRMAA. This is worth knowing about. Bindings exist for popular languages, compiled and scripted, so this forms a convenient abstraction for driving your queue via scripts. It enables an easier transition between queuing software should it be required. There exists lots of server health monitoring software. They are web-based status monitoring tools that show the health of farm nodes, usually using a traffic light system to highlight any issues. It's more likely to be used by sysadmins, but helpful to debug occasional strange test failures. If you commonly experience issues due to rogue processes using CPU memory resources or flash temp filling, this type of tool is for you. Zabbix is newish and popular, but many others exist. There are lots of choices for scripting, and they're certainly not all listed here. Don't try and use them all at once. Littering your repository with different languages is not a good idea. Learning new languages and idioms is, however, a great idea, as it will help with programming in all languages, learning new patterns and using them. These are all modern scripting languages, dynamically typed apart from OCaml. Some are just-in-time compiled, and some have just-in-time implementations. All are performant, but a lot depends on application. It's about using the right tool for the right job. Python is probably the best supported, with libraries for most conceivable applications. Debuggers are available as well as profilers, for example, cprofile for Python. Python also has a just-in-time compiled version called PyPy that can return large performance increases in certain applications. Ruby also has a comprehensive library support, including profilers, debuggers, and just-in-time compiled implementations as well. If functional languages are your thing, try OCaml, which does have support for imperative features too. It's claimed that using OCaml will cause you to develop the code faster, and it will contain fewer bugs. I find that learning functional languages really improves general programming skills too. Lua is the most famous scripting language to come out of Brazil. It's extensively used in the game industry because of its small memory footprint. It's also meant to be one of the fastest dynamically typed scripting languages. I've found Swig to be an excellent tool, the simplified wrapper interface generator. It ports a C or C++ API into a scripting language automagically. I find that a little wrapping is then required to match the scripting language idiom, but one can glue together application libraries with a top-level script to do script-like work in a scripting environment with performance work in a faster C implementation. Plus, you can often turn around top-level changes without recompilation. I use Swig, Verilog VPI, and Python as a command shell for Verilator. One can use them exactly. One can then use exactly the same code in the full state event-driven simulator. Having also written verification code in C++, that API can also be swigged and driven by Python 2. The resulting framework removes the requirement to text pass any simulation output, as pre-post simulation scripts can be called from within the simulation executable with direct access to Verilog and test C++ structures. And just finally, JavaScript, as it's being widely talked about, it's just-in-time compiled and very fast, although the library support is not currently extensive but is improving. Data visualization was GNU plot or spreadsheets perhaps, or even text. OpenOffice does have a scripting plugin. But everyone is used to browsing with a web browser, so I see this as the new GUI. It's probably the best current way to share data like regression and coverage results, as the whole team can see and interact with it using hyperlinks. Table sorting, drag and drop, and so on. I've found Chromium from Google to be the fastest at rendering large data sets, although others are improving all the time. But as it is a client, you'll need a server. Apache is far too big and overpowered. Micro web frameworks are ideal for the traffic this sort of application will see, but are scalable and can be beefed up if required. They can be run in user space, so anyone can prototype in a very lightweight. Bottle is a single Python file. Unicorn is for Ruby. There are lots of examples across the web to help craft a solution. Template engines can replace endless seas of print or write commands that input HTML. JavaScript libraries help with client-side scripting, creating interactive pages, reducing page requests, and server load. Modern browsers are very fast at dynamic rendering, so doing some work within the client works well. jQuery is just one of those available, but it's probably the most widely used, hence has the best third-party support in the form of plugins. Could be graphing like Flot or micro-templating like jQuery 2. Also available things like MooTools, Dojo Toolkit. So you're already using the file system to store data, but the lack of indices can make finding the data you're looking for slow in larger data sets, and how to avoid race conditions with multiple writers or synchronizing readers. Stop faffing about with that and use a tool that was made for such a situation. Let it worry about sorting out the races and how best to aggregate data. Although not all strictly ACID compliant, these relational databases work well enough, and we're not running applications where losing track of real money hurts. SQLite is an embedded database with bindings for scripting languages in C++. It's widely used. Using one of MySQL or the forks means you get high performance with fast asynchronous data upload. It has great support for third-party tools, but you do have to learn SQL. You can keep all your data over a project's lifetime and mine it for triage, trends, and historical events. Don't worry about data size and performance. I've always been surprised at the speed of queries on large data sets. Also available are PostgreSQL and Drizzle. Drizzle is a fork of MySQL for the cloud. It's meant to be fast and scalable. I've used MySQL for coverage databases. I think this has been independently invented a number of times. Wilson does offer a tool on his Variable site that does exactly this. NoSQL has become big in recent years. Schema-free document stores with indices to aid searching. MongoDB is the one I've used. It has a JavaScript and JSON interface. The application was storing simulation log files for triage, fail history, and other mining purposes. Sedna development seems to have gone quiet. The web seems to be moving away from XML. But I successfully used Sedna with a large architectural coverage database, several gigabytes in size, querying for tests that exercised a specific functionality. Last slide. Other tools I don't know much about, but I do like the idea of. A quick mention for GNU Octave. I've not used it at all, but it can be a replacement for MATLAB. The lack of license restrictions makes it very scalable. I'm really interested in the concept of a scalable private cloud or compute farm composed of redundant commodity hardware. It's 3 terabyte disks are now £100. How do we use those instead of an expensive network attached storage? We can add new hardware as required with tape-out schedules and plan obsolescence coincident with the release of new technology such as high-capacity disks and faster, denser processors. Ceph is a distributed file system that runs on exactly this type of hardware. Hadoop is a re-implementation of Google's MapReduce. This could be used for regression. It comes with its own distributed file system. I'd be interested to know if anybody is considered or is actually actively using Hadoop for regressions. And finally, the Hudson Android app has been around since 2009, but a higher resolution one would work well with a TV screen. It could be placed in key areas where it gets seen so everybody can see the current project status. So in conclusion, there are lots of freely available tooling. It's just a Google and click away. That can help you with your current project. Start trying them out now so you're able to use them in the future when they can help you. That's for me.
I don't think we have questions, no? It's quite big list.
Brilliant. So,
there's one question, actually.
Oh, so there's one online question, Rich.
Yeah, I have a question. You hear me? Yes, I'd like to know...
Was there any reason that you missed... I don't think you missed out Pearl when this was script, did you?
I missed Perl. Basically, I don't know. I just see it as being sort of older technology, and I was just trying to promote perhaps some of the newer ones. It was there on the first slide, I think, or not.
Yeah, it was there somewhere.
It was there somewhere.
Okay, I think we've run out of time, so we're just going to say a big thank you.